Hi everyone. Let us start with the basic definition. What is measurement? Okay, measurement is the comparison of an unknown quantity with the known derived quantity. And the known derived quantity is also called a unit. To understand this, for example, you wanted to buy a cloth of 10 meters of a particular width. Then the shopkeeper, he takes a scale of 1 meter and then he measures the length of the cloth which is unknown. So what he does? He compares the length of the cloth which is unknown with that of the known length, that is the length of the scale. So how he measures? So he repeats the scale along the length of the cloth to measure the whole length, a total of 10 meters. So here the scale, if you observe, okay, it will be, it looks like this, which is shown on the screen. Okay, the scale will have either 2 divisions or 4 divisions, sometimes maximum of 10 divisions. And this scale, okay, how it is used, you can see it on the screen. So this is the, just say, okay, the 1 meter scale. Only 2 divisions are shown. Okay, it starts with 0 and here it is 1 meter. Okay. And to measure the length of the cloth, okay, just say there is a cloth which is in green color shown here. Okay, so he repeats the scale along the length of the cloth. So from starting of the scale to the end of the scale, from first end to the second end, it is 1 meter. Then he measures the second meter, that is from the ending of the first meter. So this gives 2 meters. And then the third meter, again it starts at the end of the second meter. Then this gives the third meter. So this total is 3 meters of cloth. So here the unknown length of the cloth is compared with the known length of the scale. Okay, this is how the measurement is done. So every physical quantity is measured in the same way. Okay, the unknown quantity is compared with the known derived quantity. Okay, that is a unit. Okay, for in the case of a mass, it may be 1 kg or 1 gram. That is a standard unit with which, okay, and the unknown quantity is compared. And in the case of the volume, for example, okay, the milk that we buy, okay, half liter or 1 liter. So it is measured by using a vessel, okay, which is of 500 ml or half, that is half liter or 1 liter. Now here, if you observe, there will be either 2 divisions or 4 divisions on the scale, because the requirement of the shopkeeper is to measure either the half of the meter or 1/4 of the meter. Okay, but if you wanted to measure the length of a pen or pencil or some small object, you need further divisions. So if you look at the same 1 meter scale that is used in the laboratories, okay, it consists of 100 divisions. Okay, that is the 1 meter consists of 100 divisions. That is one division is equal to 1 centimeter, and again the 1 centimeter is divided further into 10 parts, and each part is of 1 millimeter. So then how many parts will be there on the total 1 meter? So 100 parts, that is of 1 centimeter, into 10 parts, like each centimeter consists of 10 parts. So 10 into 100, that is 1000 parts will be there. So in this case, if you look at the scale, what is the least count of the scale which is shown on the screen? What is the least count? Least count is the smallest measurement, okay, taken by the given instrument. So here the instrument is the scale. So what is the smallest measurement that we can take by using this scale? The smallest part is the 1 millimeter. Therefore, we can measure the smallest measurement, that is 1 millimeter. Therefore, the least count of the scale is 1 millimeter. Now here we measure the length of some object. So here there is the picture shown on the screen is the magnified one. Okay, the magnified picture of millimeters and centimeters, so you don't get confused here. Okay, so here there is an object of a certain length and we want to measure the length of the object. So we compare the length of the object with that of the given divisions. So we coincide one end of the object with the 0th line, and we see with what division, okay, the second end of the object coincides. So here it is coinciding with 1.8. So 1.8 centimeter or 18 millimeters. That is the length of the object we mentioned for the given object. And now we take some other object and we measure the length again. So here we do the same thing for the object B. Then in this case we find, okay, it is coming in between 1.6 and 1.7. So then we cannot give the proper length for this object, that is, it is neither 1.6 or nor 1.7. So in this case we cannot say it is of exact some length. That means what is the problem here? We need further divisions inside 1 millimeter length. At most we can divide 1 millimeter into 2 parts. Okay. But if you want more parts, it cannot be done physically, because even if it is done and drawn with by certain technology, we cannot see with the naked eye. That is the problem here. To overcome this, we use Vernier calipers. Okay, Vernier calipers, it divides 1 millimeter into 10 parts. So what is the meaning then? What is the least count? What is the 1/10 of 1 millimeter? That is 0.1 millimeter. Okay. So here, this is the instrument we use for measuring more accurate length compared to the normal scale that we have seen in the previous slides. Yeah, this is the Vernier calipers. You can see. This is how it looks. It is also of same length. If you compare with the normal scale or 15 centimeter scale, okay, you can see the size. You can compare the sizes of the two scales. Okay, it is almost comparable with the size of the normal scale. Okay. Now we'll just see a part by part. So Vernier calipers. What is Vernier calipers? It is an instrument which uses the combination of two scales. One is the main scale, the other one is the Vernier scale to measure the length. So here the two scales are these. Okay, this is the main scale, and the part which is sliding over the main scale, that is the Vernier scale. The divisions on the main scale, okay, you can see on the screen, they are same like the normal scale. That is, there are 10 divisions here in centimeter, that is 10 centimeters, but normally it will be up to 15 centimeters. And every centimeter again divided into 10 parts, that is there are 10 millimeter divisions inside the centimeter. Now these divisions are called main scale divisions. They are also indicated by MSD. Now the second scale, that is the Vernier scale, okay, which is sliding over the main scale, that is called the Vernier scale. And you can see that there are 10 parts on the Vernier scale, and these Vernier scale divisions, they are also indicated by using VSD. And this scale, okay, it can slide over the main scale. You can see it on the screen. Okay. Now, if we see the next part, the first part is the main scale, the second part is the Vernier scale, and the third part is the external jaws. Okay, the jaws that you see at the lower part of the main scale, that is J1, J2, these are the external jaws. Okay, the external jaws are used to take the measurement of the external dimensions. For example, if you are having a ring, and if you want to measure the outer diameter of the ring, then the ring is inserted between the two jaws J1 and J2 as shown in the figure, such that the two jaws are touching exactly the outer ring, the outer circle of the ring. Now we go for the internal jaws, that is the fourth part. Okay, they are denoted by using J3, J4. These internal jaws are used for measuring internal dimension. That is the reason the name is given as internal jaws. To understand like how these jaws are used, okay, you take a cylinder or cylindrical object which is having some thickness. Okay, so now to measure the outer diameter, that means we need to take the diameter of the outer part. Okay, that is denoted by D out, that is the diameter of the outer part. Or simply you can, if you just look at the one side of the cylinder, okay, the diameter of the outer circle, okay, that is the outer diameter. Now you can see one more circle inside the outer circle, and the diameter of that circle is, the inner circle is the inner diameter, that is denoted by d in. Now to find out the outer diameter, we need to place the cylinder in between the just J1 and J2 as shown in the figure. The reading on the Vernier calipers gives the diameter of the outer diameter of the cylinder. Now to find the inner diameter, we need to reverse the cylinder and insert in such a way that the two jaws, that is J3 and J4, are the inner jaws, should touch the inner circle exactly on the opposite sides. Okay, the reading on the Vernier calipers gives the diameter of the inner circle or the inner diameter of the pipe. Okay, now there is one more part, okay, which is also as important as the two jaws, that is internal and external jaws, that is the tail. Okay, this part is used to measure, okay, the depth of the hollow parts which are inside the given objects. For example, if you wanted to find the depth of the cylindrical structure or a tube, okay, we cannot place these two jaws inside the hollow part. In that case, if we use the tail, the tail moves along with the Vernier calipers. Whatever the distance it covers on the main scale, the same distance will be covered by the tip of the tail. Okay, therefore, the reading on the Vernier calipers gives, okay, the depth of the hollow part of the cylindrical structure or the tube. Okay, to understand this one, okay, for example, if you are having a tube or cylindrical structure which is having some kind of hole up to certain distance, not from the top to bottom. So in that case, if you wanted to find the outer length, okay, what is the total length of the given pipe or cylindrical structure? So in that case, we measure the length by using the two jaws. Okay, that is external jaws J1 and J2. But if you wanted to find what is the depth of, or what is the length of the inner, the hole inside the cylindrical structure, okay, we need to insert the cylindrical structure something like this. And here, okay, the top or one side of the cylindrical structure should be in touch with the main scale, and the bottom or the tip of the tail should touch the bottom of the hole. Okay, so the reading on the Vernier calipers in this case gives the depth of the hole inside the cylindrical structure or the hollow part of the cylinder. Okay, the next one, the principle of the Vernier calipers. Okay, now till now we have seen the different parts and how they are used and for what purpose they are used. Now the main part, okay, that is, okay, the idea based on which we use the Vernier calipers. Okay, that is the principle of the Vernier calipers. And this part is like the heart of the topic Vernier calipers. So here we need to understand like how we measure. So in case of a normal scale, I said like, okay, it has like each centimeter is divided into 10 parts, and therefore each part is of 1 millimeter. So but in the case of Vernier calipers, I said like, okay, every millimeter on the main scale can be divided into 10 parts, that is 0.1 mm. Now if you look at the magnified figure of the Vernier calipers, okay, you can see, okay, there are some 10 divisions on the Vernier calipers, and the entire like length of the 10 divisions is coinciding with the few divisions on the main scale. Okay, so now we take the line diagram of this part to understand more clearly. We take the magnified picture of this part. Here, this is the magnified picture of the main scale. So here you can see the numbers 1, 2, 3. They are not the centimeters, they are the millimeters. The 10 parts are the 10 divisions inside 1 centimeter. The first centimeter. So this is the 1 centimeter part. So just to understand more clearly, I have taken magnified picture of 1 centimeter. So there are 10 divisions. So here I have given the numbers 1, 2, 3 up to 9. So these numbers, they indicate the millimeter divisions. Now the second part, that is the Vernier scale that slides over the main scale, is shown. So here you can see again there are total 10 divisions on the Vernier scale. Now, okay, each division on the main scale, okay, that is equal to 1 millimeter. First division is coinciding and the last division is coinciding exactly. You can see here. So the 10th division is exactly coinciding with the 9th division. So here 10 Vernier scale divisions are exactly coinciding with 9 main scale divisions. So therefore this 9 main scale divisions can be written as 10 minus 1. Okay, 10 minus 1 main scale divisions. So in that case, if you take capital N as a number of Vernier scale divisions, so that is, instead of 10, if you write n Vernier scale division, that will be equal to n minus 1 main scale division, because 10 Vernier scale divisions is equal to 9 main scale divisions. So therefore, okay, in general terms, we can write n Vernier scale divisions is equal to n minus 1 main scale divisions. And this is the principle of the Vernier calipers. Here we know that the one main scale division is 1 millimeter. Therefore, 10 Vernier scale divisions will be how much? 10 Vernier scale division, that is the length of the Vernier scale we say. You just also remember, okay, 10 Vernier scale division means the length of the Vernier scale, that is equal to the 9 divisions on the main scale, and each division is of 1 mm. Therefore, 9 into 1 mm, it will be 9 millimeters. Therefore, the length of the Vernier scale is 9 millimeters. And from this, you can find what is the length of one Vernier scale division. What is the length of one Vernier scale division? That is equal to, one Vernier scale division is equal to 9 by 10 millimeter, that is 0.9 mm. So here, if you just observe carefully, the first division is little small when compared to the first division on the main scale. Now if you calculate the length, it is 0.1 mm less. Okay, if the one division on the main scale is 1 millimeter, then okay, the first division on the Vernier scale is 0.1 millimeter less. Therefore, it is how much? 0.9 mm. Now here, the difference between these two divisions, that is one main scale division and one Vernier scale division, that is equal to 1 mm minus 0.9 mm, that is 0.1 mm. Okay, this difference is the least count of the instrument. Here, initially, the 0th lines on the main scale and the Vernier scale both are coinciding. Now when I just open the scale such that the first division on the first line on the Vernier scale is exactly coinciding with the first line or the first division on the main scale, that is the first line is coinciding with the first line. Look at the scale carefully. So whatever the difference that you see, that is 0.1 mm, and now it is created between the two zeros. So in the case of a Vernier calipers, we are taking the measurement, means okay, we always find the distance between the two zero lines. One zero line is the zero line on the main scale, the other one is the zero line on the Vernier scale. So here, whatever the gap that is created between the two jaws, that is equal to the 0.1 mm. That is equal to the gap between the two zero lines. Therefore, this is the least measurement that can be taken by using Vernier calipers. So therefore, this is the least count of the Vernier calipers. And this gap between the two jaws is equal to the difference between the two division, that is one main scale division and the one Vernier scale division. And we calculate, how do we calculate? And this gap is equal to, okay, here the first divisions are coinciding and the gap that is created is 0.1 mm. Therefore, if you insert a sheet which is having a thickness of 0.1 mm, that can be calculated by using the Vernier calipers. Vernier coinciding division here is 1, and the least count already we have calculated, that is 0.1 mm. Okay, the total reading will be the least count into the Vernier coinciding division, that is 0.1 mm. Okay, now if we open further such that the second division is coinciding, or the second line is coinciding with exactly with the second line. Okay, therefore the Vernier coinciding division is 2 and the least count is 0.1 mm. Therefore, okay, the reading or the gap between the two jaws, that is equal to 2 into 0.1, that is 0.2 mm. So here the gap between the two zeros, okay, this one, okay, two zeros will be 0.2 mm. So therefore, the distance between the two jaws will be 0.2 mm. So same thing will be happening. So when the third division is coinciding, the Vernier coinciding division will be 3 and then the least count is 0.1. Therefore, the gap between the two zero lines will be 0.3 mm. that is the gap between the two jaws. Similarly, okay, for the fourth division, when they are coinciding with each other, so you get the distance between the two zero lines, that is 0.4 mm. And then for the fifth one is 0.5 mm. So here normally if you take a normal centimeter scale, a normal scale, so in that case we know that okay, 1 mm the length of the smallest division. Okay, now that smallest division, okay, we have divided into 10 parts by using okay, a sliding scale, okay, on the main scale, and that too in a very simple manner. When the 10th division on the Vernier scale is coinciding with the last line, that is 1 centimeter line, the zero line is coinciding with the first line on the main scale. Now whatever the distance between the two zeros you find here, okay, that is the gap between the two jaws, that is 1 mm. Now it is crossing 1 mm line. So here we know this one, this distance, okay, 0 to 1, that is 1 mm. Now we need to calculate the remaining distance, that is the 1 to 0, gap between the two red lines that is shown on the screen. So here this is 1 mm. Again we need to take the coinciding division, okay, that is Vernier coinciding division, that is first one, okay, n is equal to 1, and the least count is 0.1. The reading we take on the main scale, that is called main scale reading, that is 1 mm, and to which we need to add the distance between the two red lines, that can be calculated from the formula n into LC. So therefore the total reading or the total gap between the two jaws, that is the gap between the two zero lines, that is equal to main scale reading plus Vernier coinciding division into least count. So that gives 1.1 mm. I hope you have got the clear idea. Okay, now we find out the least count expression in simplified form. For that we take the principle of the Vernier calipers. The principle is n Vernier scale divisions is equal to n minus 1 main scale divisions, and also we take the least count formula equal to 1 main scale division minus 1 Vernier scale division. Now from the first expression, okay, we can find out okay, what is 1 Vernier scale division. We already have n VSD is equal to n minus 1 MSD. From this we can write the expression for 1 VSD, that is 1 VSD is equal to n minus 1 divided by n into MSD. Okay, now you substitute this expression 1 VSD in the second expression. Okay, that is least count, that is equal to 1 MSD minus 1 VSD, that is n minus 1 divided by n into MSD. Now you take the MSD common. So what will you get? 1 minus n minus 1 divided by n into MSD. Okay. Now if you simplify further, you will get so n minus n plus 1 divided by n into MSD. So if you simplify further, okay, this n and n gets cancelled, then you will be remaining with okay, MSD, the main scale division, 1 main scale division divided by the total number of Vernier scale divisions. Okay, so this is the simplified expression for the least count of the Vernier calipers. That is, least count is equal to 1 main scale division divided by the total number of Vernier scale divisions, that is capital N. Now, if the given Vernier calipers is a standard one, so in the case of a standard Vernier calipers, in the case of a standard Vernier calipers, 1 main scale division, that is equal to 1 mm, and number of the Vernier scale division, that is total number of Vernier scale division, that is equal to 10. So therefore, in this case, the least count will be okay, 1 mm divided by 10 that is equal to 0.1 mm. And now we find the principle of the given vernier calipers, as well as we also calculate its least count. In industries and laboratories, with the vernier calipers that are used, they are more precise compared to the standard one. Okay, if you see the first example, the vernier calipers given here, it consists of 20 vernier scale divisions, and if you see the divisions inside meter, there are total 20 divisions. So here just I write the principle, the general form of the principle. Okay, that is n vernier scale divisions, it is equal to n minus 1 main scale divisions. So here the total number of vernier scale divisions, they are 20 vernier scale divisions. So it must be equal to 19 main scale division. Just we check whether they are 19 or not. So here since each centimeter is divided into 20 parts, then okay, each part will be of 0.5 mm. There are 20 parts inside 1 centimeter. Therefore, this must be okay 19th division or 19th line. Okay, so therefore it is equal to 19 main scale divisions. Now we calculate the least count. The formula for least count is what? The least count is equal to 1 main scale division, that is divided by the total number of vernier scale divisions. Therefore, least count is equal to 1 main scale division, it is 0.5 mm, divided by the total number of vernier scale divisions, they are 20. Therefore, it is equal to 0.025 millimeter. Now we see the second example. So this is a kind of vernier scale that you see on a traveling microscope. So if you see here, there are total 50 divisions on the vernier scale, and each centimeter on the main scale is divided into 20 parts. So the biggest task in the case of a traveling microscope is to observe the readings, because there are 50 divisions on the vernier scale. So it will be very difficult to find out like which division is exactly coinciding, or which line is exactly coinciding with the main scale line. So here first of all we write down the principle of the given vernier calipers. So here if you see there are total 50 divisions. So first I write down the general form, that is n vernier scale divisions, that is equal to n minus 1 main scale divisions. So now if you see the vernier scale division, there are total 50. Therefore 50 vernier scale divisions, that must be equal to 49. According to the formula, it must be 49. We check whether it is 49 or not. So here in total, like 1 centimeter distance, there are 20 parts. Therefore up to here, up to this first red line, there are 10 lines, and up to 1 centimeter, okay, 20 lines, and then 30, second red line, 30 divisions, and then up to 2 centimeter, there are 40 divisions, and by the third red line, it must be 50 divisions. So one less than the 50th division. Therefore this is the 49th division. Therefore 50 vernier scale divisions, that is equal to 49 main scale divisions. So this is the principle, and we calculate the least count. So least count formula, that is least count is equal to 1 main scale division divided by total number of vernier scale divisions. So here we substitute the values. Okay, least count is equal to 1 main scale division. Okay, since the 1 centimeter is divided into 20 parts, therefore each part or each division will be of 0.5 mm. Therefore 0.5 is 1 main scale division divided by 50. 50 divisions on the vernier scale. Therefore 50. Okay, this is equal to 0.01 millimeter. Here now we learn about the zero error of the vernier calipers. Okay, before calculating that zero error of the Vernier calipers, okay, we learn what exactly is the zero error of a measuring device. To understand the concept of zero error, okay, we take a simple tape, a measuring tape. Okay, consider that it is having the divisions in inches, and we are looking at a small portion of the tape that is up to 16 inches. Now, if we measure by using this tape, okay, a box of length 15 inches, okay, therefore it will show exactly 15 inches because it starts with 0. Okay, there is no shift in the 0 of the measuring tape. Okay, and the measurement taken with this type of tape will be accurate. Okay, we don't take any incorrect readings as it starts with the 0, and it is said to have no zero error, and therefore there is no need of any correction for the readings that are taken by using this tape. And if it is having a zero error, then there are two possibilities. The first one is positive zero error. Okay, to understand positive zero error, you just consider the same tape and you just imagine that the beginning portion of this tape is damaged. It gets cut off. Now, and if you use this tape for measuring the length of the same box, then it will be showing 16 inches instead of 15 inches. The reason is, okay, the zero of the tape, the measuring tape, it has shifted forward by 1 inch. Therefore, the reading that is measured by using this tape will also be forward by 1 inch. Okay. Therefore, the reading observed will be 16 inches. This type of measuring tape is said to have a positive zero error, and it needs a correction. So we know that the length of the missing part is 1 inch. Therefore, the correction for the observed reading, that is 16 inches, will be 16 minus 1 inch. The reading will be 16 minus 1, that is equal to 15 inches. And the error was positive. Okay, therefore the correction will be negative. That means we have subtracted 1. Now, okay, we go to the second type of the zero error, that is a negative zero error. So in this case, you consider the same tape and you just imagine that there is a small part or extra bit of length that is added at the beginning of the tape, and that extra bit of length is 1 inch. Okay, so in that case, and if you measure the length of the box by using this tape, okay, instead of 15, it will be showing 14 inches. The reason is that the zero of the measuring tape, it has shifted backward by 1 inch. Therefore, the reading observed will also be shifted backward by 1 inch. Therefore, the observed reading will be 14 inches. Okay, this type of the measuring tape is said to have negative zero error. Therefore, the correction will be positive. Since we know the length of the extra part that is added at the beginning of the scale, that is 1 inch, therefore the correction will be, okay, the 14 inches plus 1, that is equal to 15 inches. Okay, so therefore the zero error occurs whenever the zero of the measuring device shifts either backwards or forward. Okay, so if it is shifted forward, then it is said to have a positive zero error. Then we need the correction, that is negative. So if the zero of the measuring device, if it is shifted backward, okay, then it is said to have a negative zero error. Then it needs a correction, that is positive. So now we apply the same concept of zero error to the device, that is Vernier calipers. If you are taking a reading by using a Vernier calipers, okay, that means you are exactly finding the length between the two zeros. That is, one zero is on the main scale, the other zero is on the Vernier scale. So if the given Vernier calipers is not having any error, that means, okay, both the zero lines should coincide with each other when the two external jaws are in contact. And whatever the reading that you take by using this kind of Vernier calipers, it will be accurate. Now, if these zero lines are not coinciding with each other, then there are two possibilities. Okay, either Okay, the 0 of the vernier scale, it is on the left side of the 0 of the main scale, or the 0 of the vernier scale is on the right of the 0 of the main scale when the two jaws are in contact. Okay, these are the two possibilities. Okay, now we see the positive 0 error. In the case of a positive 0 error, when the two jaws are in contact, the 0 line on the vernier scale is on the right side of the 0 line of the main scale. So in this case, okay, the vernier calipers is said to have a positive 0 error. Same like in the case of measuring tape, okay, the 0 of the measuring tape was shifted forward by some length. Then the tape was said to have some positive 0 error. The same thing here. So here the 0 of the vernier scale, it is shifted forward by some length. Okay. Therefore, whatever the reading you take, okay, it will have some extra length that was exactly equal to the shifted length. So therefore, we need to correct it. That means we need to subtract that extra length. So here we need to find out what is that extra length that was shifted forward. Okay. So here what the shifted length, okay, that is the length equal to, okay, this gap. Okay, the gap when the two jaws are in contact, there is a gap between the two zeros. Okay, this gap, okay, shifted forward. Therefore, we need to find out this length. Okay, and then you need to subtract from the final reading, the observed reading of the vernier calipers. Okay. So to find out this reading, so we know that, okay, how to find out this length. Just find out which division on the vernier is exactly coinciding with the main scale, and then you multiply with the least count. That's what we have done when we are learning the principle of the vernier calipers. Okay. So here the positive 0 error of this vernier calipers is, okay, the division that is exactly coinciding. Okay, it can be any division. So here, for example, it is showing 1, 2, 3 here. And if you generalize, okay, you can take small n, okay, that indicates, okay, the division on the vernier scale that is coinciding with the main scale, and least count of the vernier calipers. That gives the positive 0 error of the vernier caliper. And what we need to do? We need to subtract this length from the observed reading. Okay, then the correction will be negative. Therefore, the negative of n into LC, that gives the correction of the vernier calipers, which is having a positive 0 error. Now we go to the second case. Okay, so if the 0 line of the vernier scale is on the left side of the 0 line of the main scale, so in that case, what happens? Okay, so if both are coinciding, there is no problem. Now if it is on the left side as shown in the figure, then it is said to have a negative 0 error. What is the reason? Because the 0 is shifted backward, okay, by a small length. Okay, so this is the length. Then how do we find out this length? Okay, not like in the previous case, because in the previous case we have counted, okay, the division, okay, which is on the vernier scale, which is coinciding with the main scale from the left side. We have counted like this, 1, 2, 3, like this. And if you do the same thing here, okay, you will not be finding this length. You will be finding this length. Okay, you will be finding the length between the 0 line on the main scale and the first line on the vernier scale. So what we need to do, just if you observe, okay, the 10th division, it is also shifted backward. So you need to find out this length, which is exactly equal to, okay, the length or distance between the two zeros. So in that case, okay, the division that is coinciding is just say this one, 8th one. Okay, if you count from the left side, it is 8th one, but if you count from the right side, it is 2nd one. How do you get this this division? So here the total number of divisions are how much? 10. Then you subtract, okay, the division number from the total number of division, that is 10 minus 8. Okay, this is how you get the division on the vernier scale, which is coinciding with the main scale. So here 10 is the total number of vernier scale division, therefore it is denoted by capital N. And 8 is the division on the vernier scale, which is coinciding with the main scale. If you are counting from the left side, it is denoted by a small n, and into the least count. Okay, so therefore the negative 0 error for this type of vernier calipers, okay, that is equal to okay, n minus n into the least count, and since the error is negative, so we need to put minus. What will be the correction? Positive, and the correction will be, okay, plus n minus n into the least count. Okay, now we see the measurement procedure, okay, using a Vernier calipers. So when the Vernier calipers is given, or when it is used for taking some measurement, so first thing is you need to check for the zero error. So you need to check whether it is having some zero error or not. So if it is not having any zero error, then well and good. You don't need to do anything. You take the reading directly. So if it is having zero error, then you need to find out which kind of zero error it is. If it is a positive zero error, then you note down the zero error, and also you note down the correction to be made at the end of the each measurement. So if it is a negative zero error, again you need to do the same thing. Note down the zero error, and then also note down the correction to be made, okay, at the end of the each measurement. Now determine the least count of the given Vernier calipers. So that you can do by using two formulae, either by using the first one, that is 1 main scale division minus 1 Vernier scale division, for which you need to calculate, okay, both the values, 1 main scale division as well as 1 Vernier scale division. Okay. Otherwise, the simplified formula we have, that is least count is equal to 1 main scale division divided by the number of Vernier scale divisions. And if the given Vernier calipers is the standard one, okay, just remember that, okay, in the case of a standard one, 1 main scale division is of 1 mm, and the number of Vernier scale divisions, that is 10. Therefore, it will be 1 by 10, that is 0.1 mm. Okay. Now place and fix the object tightly between the jaws. Okay, if it is for the external dimension, then you place between the two external jaws. So if it is the internal dimension, then okay, you place the object in between the two internal jaws. Otherwise, if it is the depth of the hollow part of the object, then in that case you need to use the tail of the Vernier calipers. Okay, so once it is fixed, so for example, in this case, we take the object for which we need to find out the external length. So for that, we need to place the object between the two jaws, and then we need to fix the object tightly between the two jaws, and we take the readings. So we need to find out the length of the given object. What is the meaning of length of the given object? Just remember that we are finding the distance between these two zeros, this 0 and this 0. Okay, now if you look at the main scale, already we know some length, that is 2.1 mm, but we don't know this length. Okay, from 2.1 to the 0 of the Vernier, that is we need to find out here. Okay, now the total length of the object is the combination of two readings. Okay, that is total length is equal to the main scale reading that we note down from the main scale plus the Vernier scale reading. Okay, that is the part, a small gap between 2.1 and 0, and that is calculated by using the Vernier coinciding division into the least count. So now 2.1 mm is the main scale reading, and Vernier coinciding division, it is 6. Okay, this one, 6th division, into the least count, since it is having 10 divisions and main scale division is of 1 mm. Therefore, the least count is 0.01 mm. Therefore, 6 into 0.01, that gives 0.06. Therefore, total reading will be 2.16 centimeter or 21.6 millimeter. Okay, this is how we take the readings using Vernier calipers. We have seen the measurement procedure for using the Vernier calipers. Let us now take the measurements using Vernier calipers practically. So I have a Vernier calipers. You can see that the main scale, okay, this is the main scale, which is having the divisions mainly in centimeters on the lower side and then in inches on the upper side. So we mostly use the centimeter divisions, and each centimeter is further divided into millimeters. There are 10 divisions for every centimeter. Therefore, the smallest division on the main scale is 1 millimeter. Now, if you see the Vernier scale is having the 10 divisions. Now, if you follow the measurement procedure, what is the first step? So we need to find out the zero error of the given Vernier calipers. So for that we have to close the two jaws. That means the two jaws should be in contact, and then we need to check the alignment of the zero of the vernier scale with the zero of the main scale. So if you see the alignment, the zero of the vernier calipers is exactly coinciding with the zero of the main scale. Therefore, there is no zero error for the given vernier calipers. Next step is to calculate the least count of the vernier calipers. We have seen that the smallest division on the main scale is 1 mm, and there are 10 divisions on the vernier scale. Therefore, the least count of the vernier calipers, that is equal to 1 main scale division, or the smallest main scale division divided by the number of vernier scale divisions, that is equal to 1 by 10, that is equal to 0.1 mm. Now, I have an object for which we are going to take the measurements. So for this object, we can find the total length of the pipe, and we can also find the thickness of the pipe, for which we need to take the readings for external diameter and then the internal diameter, so that I can find out the thickness of the pipe. Now if you observe the pipe properly, there is a circular disc kind of obstacle lying somewhere in the middle of the length of the pipe. So you can see from both the sides. So we can find out the thickness of the circular disc that is lying somewhere in the middle of the pipe. For which what we can do is we can find out the depth of the disc, or the position where it is lying exactly from both the sides. If you add both the depths and subtract it from the total length of the pipe, you can find out the thickness of the disc kind of thing. Okay, now we go for the measurements. So first of all, we take the measurements for the length of the pipe. Okay, next we go for external diameter and then the internal diameter, and then we find out the depths, okay, from both the sides. Okay, the first one. So for finding the total length, you place the pipe and then fix the two jaws. Now we take the readings here. So if we observe the readings for finding the length of the pipe, you can see that the zero of the vernier scale is exactly coinciding with the 5 centimeter line. Therefore, the length of the pipe is exactly 5 centimeters. So here we don't need to calculate the reading for the vernier scale. So here the exact length of the pipe is 5 centimeters. Now we go for the external diameter. So for finding the external diameter, you place the pipe between the two jaws like this, and then we take the measurements. So now if you observe the scale, you can see that the main scale reading is 1.5 and the vernier coinciding division is 9. Now we go for the internal diameter. For that, we need to insert the pipe on the two internal jaws and then open the jaws. And if you observe the two jaws, they should be touching exactly on the opposite sides of the internal part. Now we take the readings. The main scale reading is 1.2 and the vernier coinciding division is 3. Now we go for the depth. For finding the depth, I just place the pipe and then I close the two jaws until the pipe comes in contact with the main scale. Now we take the readings for this depth. The main scale reading is 2.4 and the vernier coinciding division is 1. Okay, now I reverse the pipe and then I find out the depth one more time. So for this, we take the readings. The main scale reading is 2.4 and the vernier coinciding division is 6. So by using these readings, now we are going to find out the thickness of the pipe and then the thickness of the circular disc that is lying somewhere in the middle of the length of the pipe. Now we go for the calculation part. I have shown all the readings in a tabular form. We also note down the least count of the vernier calipers, that is 0.1 millimeter or 0.01 centimeters. And this picture you can see on the left side, that shows the cross section of the pipe for which we have taken the measurements using the vernier calipers. We have taken the readings to find out the length, that is capital L, of the pipe, and the external diameter, that is D1, and then the internal diameter, that is D2, and also we found depth from both the sides of the pipe, that is D1 and D2. And here, after finding the diameters, we also find out the thickness of the pipe, that is D1 minus D2 by 2. And by using the depths, that is small d1 and small d2, we find this thickness, okay, that is denoted by small t. So we have taken the measurements to find out the height of the pipe, external diameter, internal diameter, and then the thickness of the pipe, and then the thickness of the circular disc. So we have the readings of main scale as well as the vernier scale. To find out the total reading or for the final measurement, we need to add both the readings. And the vernier scale reading is calculated by using the multiplication, that is vernier coinciding division, with the least count. And we write down the formula, that is the total reading is equal to main scale reading plus VCD into LC. First of all, we find out the length of the pipe. So here, for finding length of the pipe, the main scale reading is 5 centimeters plus the vernier coinciding division is 0 into the least count, that is 0.01. I am taking in terms of centimeters. Since the vernier scale reading is 0, therefore the total reading will be the main scale reading itself. Therefore, the length of the pipe is 5 centimeters. Next, we go for the external diameter. To find the external diameter, we take the main scale reading, that is 1.5 plus vernier coinciding division, that is 9, into the least count, that is 0.01. Therefore, okay, the reading will be 1.5 plus 0.09. Okay, therefore the external diameter will be 1.59 centimeter. 1.59 centimeters. Next, we go for the internal diameters. So to find the internal diameter, we write down the main scale reading, that is 1.2 plus VCD, that is 3, into the least count 0.01. Therefore, it will be 1.2 plus 0.03, that is equal to 1.23 centimeters. Okay, so internal diameter is 1.23 centimeters. Now, by using these two readings, that is the external diameter and the internal diameter, we can find out the thickness of the pipe. So here, if you subtract D2 from D1, that is D1 minus D2, that gives double the thickness. Therefore, to find out the thickness, we need to divide it by 2, that is D1 minus D2 by 2. So here, if you find out D1 minus D2, that is, okay, 9 minus 3, that is 6, 5 minus 2, that is 3, okay, 1 minus 1, that is 0.36. Divide by 2, okay, that will be 0.18. 0.18 centimeter or 1.8 millimeter. So we note down the value, that is either 0.18 centimeter or 1.8 millimeter. Now, to find out the thickness of the circular disc, we have the depth, that is D1 and D2. Okay, we calculate the D1. For that, we have the main scale reading, that is 2.4 plus the vernier coinciding division, that is 1, into the least count, that is 0.01. Therefore, this will be 2.41 centimeters. This is the value of D1. So, if you go for D2, that is main scale reading, that is 2.4 plus vernier coinciding division, that is 6, into the least count, that is 0.01. Therefore, it will be 2.46 centimeters. Okay. So here you just note down the values of D1 and then D2, 2.41 centimeter and then 2.46 centimeters. Now we need the thickness. So first add D1 and D2 and subtract d1 plus d2 from L. That gives the thickness of the circular disc, which is somewhere in the middle of the pipe. Small t is equal to L, that is 5 minus of d1 plus d2, that is 2.41 plus 2.46, that is 4.87. So if you subtract 4.87 from 5, it will be 0.13. 0.13 centimeters or 1.3 millimeters. I hope you have understood how to use the Vernier calipers and the way to take the readings and do the calculations to get the final results. Now we solve few problems from previous JEE papers. Let us go to the first question. A Vernier caliper has 20 vernier scale divisions equal to 19 main scale divisions. One main scale division is 1 mm. If the main scale reads 1.2 centimeter and 13th VHD coincides, find the final measurement. In the first sentence, it is given that 20 vernier scale divisions, okay, that is the principle. 20 VHD is equal to 19 MSD, main scale division. And one main scale division is given, that is 1 MSD is equal to 1 mm. So from this we can find out what is 1 VHD, that is 1 VHD, that is equal to 19 by 20 MSD. And since we know the value of MSD, so that is 19 by 20 into 1 mm, that is 0.95 millimeter. Now we find out the least count. Okay, least count, that is equal to 1 MSD minus 1 VHD. Okay, that is 1 minus 0.95 millimeters, that is equal to 0.05 millimeters. Next, the main scale reads 1.2 centimeter, that is main scale reading, that is equal to 1.2 centimeters, and the vernier coinciding division, say VCD, that is equal to 13. Now find the final measurement, that is say total reading. So I write it as total reading, that is TR is equal to MSR plus VCD into LC. Okay, so that is equal to MSR 1.2 centimeters, that is 12 mm, plus VCD 13 into the least count 0.05. That is equal to 12 plus 0.65. So 12.65 is the final reading, that is in millimeters. The next question is, the diameter of a spherical bob is measured using a Vernier calipers. 9 divisions of the main scale in the Vernier calipers are equal to 10 divisions of the vernier scale. One main scale division is 1 mm. So here two informations are given. The first one is the Vernier calipers principle, that is 10 VHD is equal to 9 MSD. And next one is the value of 1 MSD is also given, that is 1 MSD is equal to 1 mm. Okay, since 10 VHD is equal to 9 MSD and 1 MSD is equal to 1 mm, then it is a standard Vernier calipers. Therefore the least count is 0.1 millimeter. Now we go to the next part. The main scale reading is 10 millimeters, that is MSR is 10 millimeters, and the vernier coinciding division, that is 8th division of the vernier scale, was found to coincide exactly with the one of the main scale division. Therefore VCD is 8. Now if the given vernier calipers has zero error of 0.04 centimeter, that is a zero error, say ZE is equal to 0.04. That since it is a positive, okay, we need to put plus 0.04 centimeter or plus 0.4 millimeter. Then now we find out the total reading. Okay, the total reading gives the diameter of the spherical bob. Let's say it is D. Diameter is denoted by D. Therefore, that is equal to main scale reading, that is 10, plus the Vernier coinciding division, that is 8, into the least count, that is 0.1. Therefore, it is 10.8 millimeters. So first of all, we apply the zero error here. Since the zero error is a positive, then the corrected reading, say it is CR, that is equal to 10.8 minus 0.4. The correction will be negative here. Okay, therefore, the reading is 10.4 millimeters. Now we find the radius, say R, that is equal to diameter by 2. Okay, therefore, diameter is 10.4 divided by 2. Therefore, it will be 5.2 millimeters. And this can also be written in centimeters, that is 0.52 centimeters. But here it is given, it should be mentioned in terms of into 10 power minus 2 centimeters. So therefore, we just multiply and divide with 10 power 2. That is 0.52 into 10 power 2 and divide. Therefore, that is 10 power minus 2. That will be in terms of centimeters, because here 10 power 2 into 10 power minus 2, this value gives 1. Okay. Therefore, now we need to multiply these two. We need to combine these two. That is 0.52 into 10 power 2, that is 52. Okay, 52 into 10 power minus 2 centimeters. Therefore, the value we need to write here is 52. The next problem, the smallest division on the main scale of a Vernier calipers is 0.1 centimeter. Okay, that is 1 MSD is 0.1 centimeter or 1 millimeter. 1 MSD is 0.1 centimeter or 1 millimeter. 10 divisions of the Vernier scale correspond to 9 divisions of the main scale, that is 10 VSD is equal to 9 MSD. So from this we can find out what is 1 VSD. Okay, 1 VSD is equal to 9 by 10 MSD. So 1 MSD is equal to 1 mm. Therefore, it is 0.9 mm is the value of 1 VSD. Therefore, we can find out the least count from these values, that is least count is equal to 1 MSD minus 1 VSD, that is 1 mm minus 0.9 mm, that is 0.1 millimeter is the least count of the given Vernier calipers. The next step, the figure below on the left shows the reading of this calipers with no gap between its two jaws. That means when the two jaws are in contact with each other, okay, the reading, it is shown by the left figure. Okay, this one, the first figure. Okay, this is the first figure. So when the two jaws are in contact, so you can see that the zero line on the Vernier scale is on the left side of the zero line of the main scale. Therefore, this device is having a negative zero error, that is negative zero error, say it is minus ZE. Okay, that is equal to, we need to find out the negative zero error. So for finding negative zero error, what we need to do? We need to take the Vernier coinciding division. So here it is a 6th division, and we need to subtract from the total number of divisions. Total number of divisions, that is 10. So it is 10 minus 6 into the least count, that is 0.1. And since the error is negative, we need to put negative sign. Minus 4 into 0.1, that is 0.4 millimeter. Now the next step is the figure on the right, just say second one. The second figure shows the reading with a solid sphere held between the jaws. The correct diameter of the sphere is, when the sphere is fixed between the two jaws, okay, the reading is shown by the right side figure. So here you can see that from the second figure, you note down the values of the main scale reading, that is MSR, that is equal to 3.1 centimeter or 31 millimeter, and the Vernier coinciding division, that is VCD, the first line is coinciding, therefore VCD is equal to 1. Now we find out the total reading, that is the diameter of the sphere. The total reading, just say TR, that is the diameter, say D, that is equal to MSR 31 plus VCD, that is 1, into the least count, that is 0.1. Okay, that is equal to 31.1 millimeter. Now here the negative zero error is minus 0.4 mm. Therefore the correction will be positive, that is plus 0.4 mm. Now we find out the corrected reading, say it is CR, that is corrected reading, is equal to 31.1 plus 0.4, that is equal to 31.5 millimeters. Now in centimeters, that is divided by 10, 31.5 divided by 10, that is 3.15 centimeter. So from the given options, the C is the correct option. Next question. In a Vernier calipers, each centimeter on the main scale is divided into 20 equal parts. If 10th Vernier scale division coincides with 9th main scale division, then the value of the Vernier constant will be. That means we need to find out the least count of the Vernier calipers. Least count. So here each centimeter on the main scale is divided into 20 equal parts. Therefore, one main scale division, 1 MSD, is equal to 1 centimeter divided by 20, that is 0.05 centimeter or 0.5 millimeter. Okay, what else is given here? 10th Vernier scale division. 10th division is coinciding with the 9th division on the main scale. Therefore, 10 Vernier scale divisions is equal to 9 main scale divisions. So from this we can find out the value of 1 VSD, 1 Vernier scale division, that is equal to 9 by 10 main scale division. So since we know the value of main scale division, we can substitute here, that is 9 by 10 into main scale division, that is 0.5. Okay, 9 into 0.5, that is 4.5, divided by 10, that is 0.45 millimeter. Okay, now we have the values of 1 MSD and 1 VSD. Therefore, we can find out the least count, that is least count. The least count is equal to 1 main scale division minus 1 Vernier scale division. Okay, that is equal to 0.5 minus 0.45. Okay, that is equal to 0.05 millimeter. Okay, so what we need to do, we need to find out the same value in terms of into 10 power minus 2. Okay, therefore you multiply and divide with 10 power 2. So it will be 10 power 2 divided by 10 power 2. So if it comes to numerator, it will be 10 power minus 2 millimeter. So this should be taken out, and so if you multiply 10 power 2 with the 0.05, so it will be 5 into 10 power minus 2 millimeter. So this is one way. Otherwise, you can also find out, okay, least count, that is LC is equal to one main scale division, that is 0.5 millimeter divided by the number of divisions on the Vernier scale, that is 10, that is 0.05 millimeter, or 5 into 10 power minus 2 millimeter. Now we go to the next problem. The diameter of a cylinder is measured using a Vernier calipers with no zero error. It is found that the zero of the Vernier scale lies between 5.10 and 5.15 centimeters. Okay. That means these two lines are just side by side lines. Therefore, the length between these two lines gives the one main scale division. So therefore, we can find out the one main scale division here. 1 MHD, that is equal to 5.15 minus 5.10 centimeters. Okay, so it will be how much? 0.05 centimeters, or in millimeters it is 0.5 millimeters. Okay. And the next line, the Vernier scale has 50 divisions equivalent to 2.45. So 50 Vernier scale divisions, 50 VSD, that is equal to 2.45 centimeters. So from this we can find out what is 1 VSD. 1 VSD is equal to 2.45 divided by 50. That gives 0.049 centimeters, or 0.49 millimeters. Next we see, so here, so since we know what is 1 MHD and the number of Vernier scale divisions 50, I think we can also find out the least count the other way, that is least count is equal to 1 MHD divided by the number of Vernier scale divisions, that is 50. So that is equal to 0.5 divided by 50. So that is equal to 0.01 millimeters. So if you find out the normal way, that is least count is equal to 1 MHD minus 1 VSD, then it will be 0.5 minus 0.49, that is equal to 0.01 millimeters. I am showing both the methods to understand the least count formula. So the next line, the 24th division on the Vernier scale exactly coincides with one of the main scale divisions. That is, the Vernier coinciding division VCD is equal to 24. The diameter of the cylinder is. So what is the MSR here? The MSR is given in the second line itself, that is the zero of the Vernier scale lies between 5.10 and 5.15 centimeters. That means if the main scale reading here is MSR is equal to the reading just before the zero line of the Vernier scale, that is 5.10 centimeter. To find out the diameter, we just need to add main scale reading and Vernier scale reading. That is the total reading, that is the diameter, just say D, that is equal to the main scale reading, that is 5.10, plus the Vernier scale reading, that is VCD into LC, that is VCD is 24, and least count is in terms of millimeters. We need to convert it into centimeters, that is 0.001. Therefore, the diameter is equal to 5.10 plus 0.024. Therefore, that is 5.124 centimeters. So, this is the diameter of the cylinder. Next problem. A Vernier calipers has 1 millimeter marks on the main scale, that is 1 MHD is equal to 1 mm. 1 MHD is equal to 1 millimeter. It has 20 equal divisions on the Vernier scale, which match with 16 main scale divisions, that is 20 PSD is equal to 16 MHD. Now for this Vernier calipers, the least count is, what is the least count here? We need to find out the least count is how much. So here one main scale division, that is 1 mm, and there are 20 Vernier scale divisions. So we have the formula 1 main scale division by 20 Vernier scale divisions. Can we use that formula? No, because one main scale division divided by 20 Vernier scale division is the simplified formula for the Vernier calipers, which is having the principle, or which is following the principle, that is n VSD is equal to n minus 1 MSD. But if you see here, n VSD is equal to n minus 4 MSD. So therefore, we cannot use the formula, that is 1 MSD by number of VSD. So here we follow the standard formula, that is least count is equal to 1 MSD minus 1 VSD. So for that, we need to find out what is the VSD value. So 1 VSD is equal to 16 by 20 MSD. Okay. So 16 by 20 MSD value is 1 mm. So therefore 16 by 20 value, that is 0.8 millimeter. So now the least count that is equal to 1 main scale division minus 1 Vernier scale division, that is equal to 1 minus 0.8, that is equal to 0.2 millimeters. The next problem. The edge of a cube is measured using a Vernier calipers. 9 divisions of the main scale is equal to 10 divisions of the Vernier scale, and one main scale division is 1 mm. So here everything is given, that is one main scale division is 1 mm, 10 VSD is equal to 9 MSD. So therefore the least count will be 0.1 mm. Next one, the main scale division reading, that is 10, and one division of the Vernier scale was found to be coinciding with the main scale. The mass of the cube is 2.736 grams, and calculate the density in gram per centimeter cube. So here the edge of a cube is measured by using a Vernier calipers, and it is having the main scale division value, that is 1 MSD is equal to 1 mm, and the number of Vernier scale divisions are 10. Okay, therefore capital N is equal to 10, and since it is following the principle 10 VSD is equal to 9 MSD, the least count can be calculated directly with the simplified formula, that is 1 MSD divided by the number of Vernier scale divisions, that is 1 by 10, that is 0.1 millimeter. And the main scale reading, that is 10 mm. So MSR is 10 mm, that is equal to 1 centimeter, and the division on the Vernier scale, that is coinciding with the one of the main scale division, that is VCD is equal to 1. The total reading, that is the side of the cube, that is equal to the main scale reading, that is MSR, plus the Vernier scale reading, that is BCD, into the least count. So here the MSR is 1 centimeter plus VCD is, that is 1, into the least count 0.01. That is equal to how much? 1.01 centimeters. This is the side of the cube. Therefore, the volume of the cube, that is equal to side cube. Okay, side cube, that is equal to 1.01 whole cube. That is equal to 1.030301. Okay, now the density is equal to mass per volume. So the mass is given here, that is mass is 2.736 divided by the volume, that is 1.030301, that is equal to 2.8189 gram per centimeter cube.